Hello everyone. For those of you who don't know me, my name is Jon Mease, and I'm happy to have the opportunity here to share my experiences in bringing GPU support to the Datashader Python library. As mentioned on the previous slide, I recently joined Plotly as their chief scientist, but prior to that, I spent the better part of a year contracting with Anaconda to work on the Datashader and HoloViews projects. The work I'm going to discuss today was funded by NASA and the U.S. Army Corps of Engineers. Here's an overview of what I'm going to cover. First, I'll introduce Datashader at a high level for folks who aren't familiar with the project. Then, I want to talk about some of the obstacles that the project has faced in the past when considering adding optional GPU support. Then I'll discuss how the RAPIDS project and the ecosystem around it has addressed these obstacles and made it feasible for a project like Datashader to provide optional GPU support. Then, I'll share a few performance results so you can get a sense of how RAPIDS integration can benefit Datashader users. And finally, I'll close with a demo of RAPIDS and Datashader in action. All right, so what is Datashader? Datashader is a high-performance Python library for generating a variety of principled visualizations of large datasets. Here are a few examples of the kinds of visualizations that you can create with Datashader. This is a visualization of over 300 million points, one for the approximate location of every person in the United States from the 2010 census. In this case, color encodes the number of people living in each location. Dark red represents regions of the country with the lowest population density, and bright yellow represents regions that have the highest population density. By default, Datashader uses a technique from image processing called histogram equalization to generate a nonlinear color scale that automatically prevents oversaturation. And here is a visualization of airline flight paths from the OpenSky flight dataset. This dataset includes over 10 million flight path coordinates. In this case, flight paths are drawn as lines that are colored red while the flight is ascending and blue while it is descending. The number of flights passing through a particular location is encoded as the opacity of the resulting image, and Datashader takes care of blending the red and blue where they overlap. Here's a visualization of the average depth of each location in the Chesapeake and Delaware Bays. The underlying dataset here is a large triangle mesh with over 1 million triangles. In addition to triangle meshes, Datashader can also work with quad meshes, where each element is a quadrilateral rather than a triangle. Quad mesh support is particularly useful in climate science applications. Here is a graph visualization of the collaboration relationships of 600,000 researchers across 15,000 UK research institutions. Given a layout for the nodes in the graph and a set of edges, Datashader can render the edges using a technique called edge bundling. This approach groups edges with similar start and end locations into thicker, brighter edges, making it a lot easier to interpret the structure of large networks. Beyond its primary function, a secondary goal of the Datashader project is to serve as a sort of case study for how to implement and share high-performance numerical algorithms in Python without resorting to using precompiled C or Python extensions. To achieve this, Datashader relies on algorithms included with the data structures provided by NumPy, Pandas, and Xarray. And for custom algorithms, it relies heavily on the Numba just-in-time compiler. And this library can transform Python functions into efficient machine code at runtime. Datashader creates images from data using a well-defined pipeline of operations, where the result of each operation is exposed to the user for inspection and customization. Data are projected into scene coordinates, then binned into a two-dimensional pixel grid. When multiple data points are binned to the same pixel, these points are combined into a single scalar value using a configurable aggregation operation like a count, sum, mean, or standard deviation. This array of aggregated values is then color mapped into an RGBA image according to a color scale and color scale projection. As I mentioned before, the default color scale projection is histogram equalization, which automatically minimizes saturation. Other color scale projections are available, including a linear, log, square root, and cube root projection. By itself, Datashader produces static images, and it doesn't draw things like axes, legends, color bars, and grid lines. For interactive use, Datashader needs to be combined with an interactive plotting library like Bokeh or Plotly. The easiest way to work with Datashader interactively in the notebook is through HoloViews, with either the Bokeh or Plotly backends. Combined with Panel, these HoloViews dashboards can also be served as web applications. Another option for including Datashader plots in standalone web applications is through the Plotly Dash project. The NVIDIA Rapids team actually recently published a really nice example of powering a Dash app with Rapids and Datashader, and I'll show a demo of this dashboard at the end of the presentation. So it's long been a goal for the Datashader project to provide optional support for GPU acceleration. But prior to Rapids, there have been two primary obstacles that made this impractical. The first obstacle is the overhead associated with data transfer. In order to execute GPU operations on data arrays, the full array must be copied from CPU memory to GPU memory. Then, in order to process the results of the GPU operation using a traditional CPU library, like Pandas or NumPy, the results must first be copied back to CPU memory. This means that every call to Datashader would have required transferring large data arrays to and from GPU memory, which would have substantially reduced or even eliminated the potential performance gains. The second obstacle is more of a maintainability consideration. Traditional GPU programming is done in C, C++, or Fortran. So here is an example of a C++ CUDA kernel that increments every element of an array by 1. But as I mentioned earlier, Datashader's internal algorithms are implemented in Python and then compiled to machine code at runtime using Numba. Here is an equivalent Python function that operates on a NumPy array, incrementing the value of each element of the array by 1. This is similar to the kind of functions you'd find in Datashader. Prior to the Rapids ecosystem, adding optional GPU support would have required writing and maintaining separate CPU and GPU implementations of all of Datashader's core algorithms. And while theoretically possible, this would have substantially increased the complexity of the code base and made it much harder to maintain parity between the CPU and GPU implementations. So enter Rapids. The Rapids project was announced by NVIDIA in late 2018, and it's quickly grown to encompass the whole ecosystem of technologies for taking advantage of NVIDIA GPUs from Python. cuDF, cuML, and cuGraph are part of the core Rapids project, which is maintained by NVIDIA. cuDF provides a Pandas-style data frame that operates directly on GPU memory. cuML is a scikit-learn style machine learning library that provides GPU implementations of most of the traditional machine learning algorithms provided by scikit-learn. cuGraph is a Network X style graph analysis library that provides graph data structures and using GPU memory and a collection of GPU accelerated operations on these graphs. Cupy provides a NumPy-style n-dimensional array based on GPU memory with GPU-accelerated operations on it. Cupy was developed as part of the Chainer project, but it's fully compatible and interoperable with the core Rapids projects. And finally, Numba for CUDA provides a just-in-time compiler to generate highly optimized CUDA kernels from Python functions. These CUDA kernels can operate directly on the GPU arrays created by the cuDF and Cupy libraries. Like the core Numba project, Numba for CUDA is developed and maintained by a team from Anaconda. So how do we avoid data transfers with cuDF and Cupy? The Rapids ecosystem solves the data transfer problem by enabling users to build and execute entire data processing, analysis, and visualization pipelines on the GPU. Now, data can be transferred to GPU memory in the form of GPU data structures like those provided by cuDF, Cupy, and cuGraph. Then, functions can be written that input and output these GPU data structures. This makes it possible for libraries like cuML and now Datashader to be used in sophisticated data processing pipelines without repeatedly transferring data to and from the GPU. And now code reuse with Rapids. The Rapids ecosystem makes it possible to implement domain logic in Python and then share these implementations across the GPU and CPU code paths. Today, most libraries in the Rapids ecosystem are designed with the goal of being used as drop-in replacements for libraries in the traditional PyData stack. So as I mentioned before, cuDF for pandas, Cupy for NumPy, and cuML for scikit-learn, cuGraph for Network X, etc. But these libraries, they require a compatible GPU to operate. In contrast, the goal for Datashader has always been to provide optional GPU support from within the existing codebase, reusing the existing APIs. Accomplishing this without introducing significant complexity requires good strategies for maximizing the amount of logic that can be shared between CPU and GPU code paths. Some of Datashader's internal algorithms are implemented using the Pandas Dataframe API. Thanks to how well cuDF follows the Pandas API, it is usually pretty straightforward to write functions that can accept either a Pandas or cuDF dataframe. For example, the top code block here shows an example of a function named filterSum that inputs a dataframe, filters it based on the value of one of the columns, and then computes the sum of the remaining rows for a second column. The middle code block shows how pandas can be used to load a CSV file into a data frame and then pass that data frame to the filterSum function. The lower code block shows how cuDF can be used to load the same CSV file into a GPU data frame, and this GPU data frame can be passed to the same filterSum function. Some of Datashader's internal algorithms are implemented using the NumPy API. And thanks to how well Cupy follows the NumPy API, it's also usually pretty straightforward to write functions that can accept either NumPy or Cupy arrays. The top code block here contains a function that inputs a 2D array of features, one feature instance per row, and returns a new 2D array of the same size that contains the result of performing z-score normalization on these features. This is a common feature scaling approach that ensures that each feature dimension has a mean of 0 and a standard deviation of 1. The middle code block shows an example of calling this function with a NumPy array, and the bottom code block shows an example of calling it with a Cupy array. As I mentioned earlier, Many of Datashader's internal algorithms are implemented as custom Python functions that are compiled at runtime using Numba. Combining Numba's CUDA support with the RAPIDS ecosystem makes it possible to use Numba to write CUDA kernels that can operate on the contents of cuDF data frames and Cupy arrays without copying and without transferring data to and from GPU memory. It also makes it possible to share implementation logic between CPU and GPU code paths. For example, the top code block here contains a simple function named increment element by 1 that operates on a single element of an input array to increment its value by 1. The numba.jit decorator tells Numba to compile this function to machine code the first time it's called. The middle code block is a function that loops over all of the elements of an array and calls the increment element by 1 function on each one. This function is also wrapped in the numba.jit decorator, and so it too will be compiled to an efficient CPU function the first time it is called with a one-dimensional NumPy array. The bottom function is a CUDA kernel that will be executed many times in parallel on the GPU. Numba makes it possible for CUDA kernel functions like this to call CPU-compatible Numba functions. And here we take advantage of this fact to call increment element by 1 from within the kernel. This CUDA kernel can then be called on a Cupy array, and it will increment the elements of the array by 1 without copying or transferring the array between CPU and GPU memory. Datashader makes heavy use of this design pattern to share significant amounts of logic between the CPU and GPU code paths. To make this more concrete, I created a complete minimal example that uses these code reuse strategies to build a one-dimensional histogram library that supports CPU execution on NumPy arrays and GPU execution on Cupy arrays. With the adoption of RAPIDS technologies, many Datashader use cases can now be accomplished 1 to 2 orders of magnitude faster than the corresponding single-threaded CPU implementations. For example, there is a 10x speedup when rendering 300 million points and up to 120x speedup when rendering large quad meshes. If you're interested in looking a little deeper, links to the benchmarking notebooks are included at the bottom of the slide. These notebooks were executed on a consumer-grade GeForce RTX 2080 Ti with 11 gigabytes of GPU memory. Thanks a lot for your attention. I hope you learned something new. I'm going to close by showing you a screencast of the Dash app that I mentioned earlier. Both this Dash app and the screencast were created by the RAPIDS team from NVIDIA. The app is available on GitHub at the link below, and is described in detail in the Medium post that is also linked below. At the time of recording, this screencast has not yet been posted publicly, but I received permission from the authors to share it in draft form here. Thank you very much.